dun, 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 2D momentum once again. Okay, so we're looking at conservation momentum again, like I said, but we're looking at it in 2 dimensions. And last time we did this, we had nice 90-degree triangles. The last time we did this, we took a look at kind of right triangles. We said like, hey, maybe a wide receiver was going south, and then a defensive linebacker was going to the west, and whenever they hit each other and they stick together, they have some final momentum. That's what we did previously within this unit. This is nice because it's at a nice 90 degrees, and we can use things like Pythagorean's theorem in order to find the hypotenuse there. But what happens when things kind of ricochet at, well, kind of random angles, right? And that's what we're going to look at in this problem. We're still going to be using the conservation of momentum. Whatever momentum we had initially is the same amount of momentum we have to have at the end. But because things are kind of ricocheting or colliding and then bouncing off in weird directions, we're going to have to look at things in the x direction and the y direction, which we've done a lot of physics where we look at things in the x and y direction before. Projectile motion, all of forces. This isn't anything new for us. It's just the first time we've really dove into it en masse for momentum. So let's take a look at this problem here. This is the second to last problem of the practice sheets for this unit. It's the first one of the E4. And because we have momentum here with an initial and a final component, let's first just start drawing our initial setup. What we have to begin with is we have a 12-gram rubber bullet. So there's the mass of our bullet. And it's moving at 150 meters per second. So there's that initial velocity of that bullet. And it strikes a 35-gram tin can. And that tin can was sitting at rest. And doing a lot of physics that we've been doing this year, we know when something is at rest, its velocity is 0. It's not moving at all. So that's a value that's kind of hidden there, but we know what it is. So let's just draw that. Let's draw the initial setup. We've got a bullet, not drawn particularly well. It has a mass, we'll call it MB, mass of the bullet, of 0.012 kilograms, because we just took that and converted grams to kilograms. And it has some velocity here, VIB, of 150 meters per second. There's a can. We know its mass is 0.035 kilograms. Just did that little conversion. And we know it has a velocity of 0. So that's our initial setup. We kind of drew a picture. We just wrote everything that we kind of knew down. Let's see what happens after the bullet strikes the can. So on our final side of things. On our final side of things, when the bullet strikes the can, it moves off in a direction 65 degrees to the left of the original direction. So let's do this first. The original direction was directly right. So I'm just going to put like a kind of dashed line going to the right. The bullet deflects off 65 degrees in that direction to the left of the initial. Kind of looks like up on our paper, but like if you were the bullet, it'd be left for it. The tin can also deflects, but it deflects down or to the right at 25 degrees. What we are looking for is how fast are these objects, the bullet and the tin can, moving after the collision. Now there's technically 2 ways we can solve this problem. The one method that we could use is what's known as a graphical momentum method. We have to pull out protractors and rulers in order to do that. We're not going to do it in this video. If you want to see an example of me doing something like that, check out other videos that I've got stored on this YouTube page. What we're going to do here is we're going to analytically solve this. We're going to solve this with numbers so that we are going to get a totally precise answer. Because whenever you use protractors and rulers, you're taking measurements. You might be a little bit off. It's a quick way, but it's not always perfect. We're going to find an exact solution here. Now, when we analytically solve this with all these numbers, the thing that we are trying to remember and trying to prove here is that the initial momentum equals the final momentum. And we've done this previously. We've normally been moving in one dimension, like left and right. When we're moving in two dimensions, left, right, like we were in the beginning, and then if we look at the final positions, or the final momentums, we actually see we're not just moving left, right, but also up and down. We could draw a little triangle here and say that, hey, this final momentum here, it's actually a combination of two things. It's a combination of some momentum moving to the right and some momentum moving up. Or, if you happen to be the bullet, or the tin can, its momentum's going down and to the right, which means it has some momentum going to the right, and it has some momentum going down. These are just vector components, which we could easily solve for using Chief SOHCAHTOA. This means that when we start thinking about our momentums here, the momentum initially in the x direction has to equal the momentum final in the x direction. And the momentum initially in the y direction has to equal the final momentum in the y direction. Before, we only really cared about one direction, so we kind of had it. But now, with two directions and solving for unknowns like this, we had to set up these momentum equations for both x and y. So we're still going to use that super long momentum equation. m1 times v plus m2 times the second velocity equals the m1 v1s plus m2's v2s again. We're still using the big long equation that we've been using, and if you haven't seen that, go check out a prior video. But we're doing this for the x direction, and then we're going to do it for the y direction as well. So let's set this up initially for the x direction. If we look at our initial momentums here, masses times velocities, we have the mass of the bullet, which is 0.012 kilograms, times the bullet's initial velocity, 150 meters per second. And forgive me for not placing in units here. These are momentums, so they will be Newton seconds. But this is going to get big. From that initial momentum from the bullet, we have to add the momentum from the tin can. And this is actually super nice. We could say mv here, but we know the initial momentum of the bullet, or of the tin can, excuse me, was 0. So anything times 0 is 0. So that was a nice one there. It just kind of went away. Now notice in this case, we only picked things going in the x direction, which the bullet was initially only moving in the x direction. That's why we included all of it. When we set this equal to the final, we only want to include the final momentums in the x directions. So we only want these purple vectors that I've highlighted here. Well, to get those, we need to use SOHCAHTOA. If we recognize that these angles are 65 and 25 for the bullet and the tin can respectively, we can also recognize that the vertical components are the opposite sides, while the horizontal components are the adjacent sides. Using our knowledge of SOHCAHTOA, we can say that this adjacent side, or the final momentum in the x direction, and this will be both for the bullet and we'll have to do one for the can. So we'll call this final momentum x direction bullet. That's a lot. That's going to be equal to the bullet's final momentum times the cosine of 65 degrees. Because that's that adjacent side, and cosine is an adjacent over an hypotenuse. So when we solve that, we get the following. This means we could write it, if we wanted to, as the mass of the bullet, the bullet's final velocity, times the cosine of 65 degrees. That's the final momentum, but only in the horizontal direction, only in that x direction that we have. If we play the same tricks for the tin can, the final momentum in the x direction of the tin can, we'll just put like a T for tin. Well, that's going to equal the final momentum of the tin can multiplied by the cosine of 25 degrees, because this is still the adjacent side of this lower triangle. So when we write that out in completeness, we see that we have the mass of the tin can, empty, multiplied by the tin can's final velocity, multiplied by the cosine of 25 degrees. So we just took, hey, look, there's some final momentum here, but I only want the x horizontal component of that momentum. And now, since we know what these values, this setup are, what these values could be, here and here, these are what we're going to add together down below in our giant x equation. So we're going to have the mass of the bullet, 0.012, the bullet's final velocity, multiplied by the cosine of 65 degrees. We're then adding to this the mass of the tin can, 0.035, times the tin can final velocity, multiplied the angle that it got shot out at. So cosine of 25 degrees. So we've got this like rather large equation now. Okay, not only is it one of the large momentum equations that we've been using, but it's even larger than normal because we've got these cosine terms in there because we wanted just the horizontal components of that equation. Now, if we look at this, a lot of the values we have here in this equation in the x direction, they're just numbers. We could put a lot of these numbers together, but we are trying to solve for the final velocity of the bullet and the final velocity of the tin can. And because these are different objects, these are different variables. We cannot just combine these together like we have in some of the problems before. They're not like terms. And this is a bit of an issue because if these are two different variables, like x and y or m and n, we only have one equation for them. And what we've seen throughout the year is that for every variable we have, for every unknown variable we have, we need another equation so that we can solve it. So with one equation and two variables, this has an infinite number of solutions. It's not solvable. We need another equation. And luckily for us, we have one. We just did this equation for the x direction. We still have an equation to do for the y direction. This is our second equation here, and using that, we can start mathematically solving things out. We are still going to say initial momentums equal the final momentums, but we only want momentums going up or down, y directions. So if we look initially at our picture, nothing here is going up or down. That bullet is only going to the right, and the tin can wasn't even moving. So our initial momentums in the y direction are 0 for the bullet plus 0 for the tin can. The bullet was moving left and right. It wasn't moving up and down. So there's 0 y momentum for the bullet. Tin can wasn't moving, so it gets a 0 as well. When we look at the y directions, though, after the ricochet, we see that we now have the opposite sides to play with. These opposite sides, when we add them together, have to add up to 0, because the initial still has to equal the final. And what that should signal to us is that if we're adding two numbers together and they have to add up to 0, one of them better be negative, right? I can't take 3 plus 9 and get a negative, and get 0. But if I take 3 plus negative 3, I could get 0 then. So we are going to have to designate a positive and negative direction here. It doesn't matter if you want up or down to be positive, but because these are momentums, they are vectors, we do need to designate positive and negative directions. Let's just take classic physics to be the name of the game and say up is positive, which makes down negative. You could flip that if you wanted. It's not going to change a thing, but let's just do it this way. If this is the case, and we want to solve these opposite sides, we want to find the momentum's final velocity in the y direction for the bullet, which that's going to be the final momentum multiplied by the sine of the angle this time, because we're looking for that opposite side, and we think of that sine is opposite over hypotenuse. So this is going to be the final momentum of the bullet times the sine of 65 degrees, which will, expanding that momentum, simply become the mass of the bullet, the final velocity of the bullet, multiplied by the sine of 65 degrees. If we do the exact same thing for the tin can, recognizing that the vertical component is indeed the opposite side, we'll also find that the final y velocity of the tin can, well, that's going to equal the same idea. It's going to be the mass of the tin can times the final velocity of the tin can times the sine of its angle, 25 degrees. And the only thing we have to remember here is we called down the negative direction, so this is actually a negative quantity, simply because we said down was negative. So we used those triangles, we used our knowledge of SOHCAHTOA, which that goes all the way back to Unit 4 when we were looking at that, so we're experts at SOHCAHTOA at this point. And we said, look, we have y components acting up and down, let's add them together and get something out of it. So if we take these quantities and we put them down into our y equation, we're going to have the mass of the bullet, 0.012, times the bullet's final velocity, multiplied by the sine of 65 degrees, plus, and then here comes our tin can, the mass of the tin can, 0.035, times the tin can final velocity, multiplied by the sine of 25 degrees. And if you're looking at this, I made a slight error here, and it's an error that you are likely to make as well. We said that down was negative. So if I'm adding that value in, I've got a bit of an issue. I need to be adding a negative quantity or subtracting that value. That is the number one spot that people make mistakes, because we start getting into the groove of the problem like we've been doing, and then you just put an addition because that's what you're used to. Direction matters, okay? But now we have two equations to solve for our two unknowns. And while these equations are indeed very large, we have done substitution methods before to solve for things like this. We've done this in forces when we had a tractor or a truck pulling a trailer, when a cheese was on the table and a mass was pulling it down like our rat. We've done problems like this. This one's just more number filled than we'd like to care for. But this is solvable. We do know how to solve it, and we have the skills to do it. So let's start churning things out and solve this out. What we're going to try to do here is we're going to take our second equation and solve it for VBF so that we can substitute values into the upper equation. So let's take a look at our bottom equation here, and let's just solve for VBF. The first thing I'm going to do is I'm going to take this entire quantity over here, and I'm going to add it to the other side. In doing so, it goes away over here, and on the left side, which was a bunch of zeros, I'm now going to have 0.035 times the final tin velocity times the sine of 25. Because that's all one quantity there. It's all just some number of the final tin velocity. I just brought it all over. And this is going to equal the 0.012 times the final velocity of the bullet times the sine of 65 degrees. And if I want to get that velocity of the bullet by itself, well, I can just divide by 0.012. And then I can divide by the sine of 65 degrees as well. That will eliminate these. They'll divide out. And I now have an equation for the final velocity of the bullet in terms of the final velocity of the tin. And this will allow me to take this entire quantity on the left here and plug it up into our first equation in the x-axis. which that's not the x-axis one. Our x-axis is all the way, whoop, all the way up there. So we're going to go back into our x-axis equation, but we're going to plug in this new quantity that we just found. So this is going to get rather large, so if you're finding that you're using a lot of paper, welcome to the club. That's how we do physics. We go through paper like there's no tomorrow. So let's write out this giant mega equation. In the x direction, we're going to have the 0.012 times 150. So we're going to get the 0.012 times the 150. There's then the plus 0, but since adding 0 does nothing, we'll just end the left side of the equation there. This will be equal to the mass of the bullet, 0.012. And now it's going to be multiplied by the bullet's final velocity, which we know is this right here. So let's write all of this new quantity out. So 0.035, the tin's final velocity, the sine of 25 degrees, and then this is all divided by the 0.012 sine of 65 degrees. And you want to be careful whenever you're doing this division on your calculators. Some people type in divide and then 0.012 times sine 65, and that actually brings the sine 65 back into the numerator. You want to be careful about that. And then don't forget, while this was just the final velocity of the bullet, we still needed the cosine of 65 degree term up here as well. So that is very big. But if you look at it, a lot of these things, they're just numbers. They're just numbers that we can multiply and divide. It's just some coefficient in front of the actual variable we care about right here. To continue this, though, we need to add to this the actual tin can's final setup. That's the mass of the tin can, the 0.035, times the velocity final for the tin can, multiplied by the cosine of 25 degrees. So a very, very large equation now. There's a lot of numbers in it, many numbers, such physics. But we are just left with one unknown variable, this final tin can velocity. Which means that if we just start compiling numbers together, we can combine these like terms. These are actually going to be combined together. This is all going to simplify very, very nicely. So let's pull out our trusty calculadoros. Well, the only thing I can trust in my life. And let's start putting numbers together. So 0.012 times 150 gives us 1.8. And that's in Newton seconds because that's a full momentum there. This is going to be equal to this whole thing up top. One of the first things I see, though, to make my life a little bit easier is this 0.012 actually divides out, which is really awesome. And something that you might see at home is that we have a cosine of 65 divided by a sine of 65. Some of you might recognize that this is actually referred to as a cotangent of 65 degrees. We've seen previously that sine over cosine can be a tangent. If you flip that, cosine over sine, it's something known as a cotangent. Well, that's a neat thing to notice. We actually don't need it here because we're still just pushing through numbers like there's no tomorrow. So let's just start cranking numbers out here. We've got 0.035 multiplied by the sine of 25. Make sure you're in degrees or else everything's going sideways. And I got 0.01479. I'm just going to keep that entire quantity here. I'm not going to do any rounding early. I'm just going to take that quantity and multiply it by the cosine of 65. I get 0.00625, blah, blah, blah. I'll then divide it by the sine of 65. And here, I get the quantity 0.00689, which let's just round that down to 0.0069, and then we still have that final velocity of the tin cup. So even though there was a lot of stuff there, we just comboed it all together and just said, woo, it's a number. Because that's all it ever was. It was just a number. So now we're going to add it to the right side here. That's 0.035 times the cosine of 25. That's going to give us a quantity of 0.032 when we round, multiplied by the tin cup's final velocity. And now if we look at this, this looks actually very straightforward. We easily see that these are like terms that we're going to add together. So let's just bring down the 1.8 again. And then let's add together the 0.0069 and 0.032. So 0.0069 plus 0.032 gives me 0.0389. We'll just call it 0.039. And then our unknown variable, the tin cup's final velocity. And at this, we should be feeling great. We've done math at this point for years. Divide by the 0.039. Divide by the 0.039. We find that the tin cup's final velocity gives us, drumroll please, 46.15, and this is a velocity, which means, since we've been in SI units the whole time, it has to be units of meters per second. So we did a bad job of carrying our units, but we know our final answer of velocity, when we do it right, has to be meters per second there. So that was a ton of work to get this tin cup's final velocity. There's a lot of math work of substituting things, but in terms of like the actual physics, we've done a lot of this before. This one just had a few more numbers. But wait, there's more. We're not done here. We need to get the bullet's final velocity as well. Which, if you're here live in the classroom, you got to see Jimmy's face. He's like, oh my goodness, when will this end? Well, it's going to end in like half a second because you've already done all the hard work. You know what the bullet's final velocity is. It's this equation. Except now, you know that the tin cup had a final velocity of 46.15. So you already did the work in order to solve this. You just need to go back up and put in all the numbers. So if we go ahead and do that now, 0.035 times 46.15, I get 1.61525, whatever, times the sine of 25 gives me 0.6826. Divide by 0.012, I get 56.886. And now I'm going to divide by the sine of 65 again. Remember, that sine of 65 is also in the denominator, so I'm dividing by the sine of 65. And we find that the final velocity of the bullet comes out to be 62.77 with some rounding meters per second. So even though there was still a second part of the problem to do, we already did all the hard work to find it. And that's exactly what happened when we did all of the other substitution methods earlier on in the year. We found out something like an acceleration, and then we just plugged it back to find a tension. And snap, we were done. So nothing's changed from what we've done earlier in the year. We've done a lot of substitution problems like this. This one just takes the cake in terms of the sheer amount of math that goes into it, simply because we had two dimensions we had to consider, and we had to break up those final momentums into an x-axis and a y-axis to conserve them. So a little bit more work than we've normally done, but in this case, we were able to apply our physics knowledge that we already know to solve them out with just a little bit of extra math. Key thing for this, other than the physics itself, if you're going through this math and you want to make sure you're doing it right, use more paper. Don't be afraid to spread it out. Don't be afraid to flip to a second page. Using more paper is always a helpful thing in the world of physics, because as problems start getting larger, as you're keeping track of many, many things, it is easy to make a mistake. And take a look at this. Like, look at how many arrows we've just got floating around here. So just make sure you're taking your time walking through this. Make sure you're doing the math correctly, and you'll come out fine in the end. If you've got any questions or whatnot, hit me up. Let me know what you think of this. If you need any help, I'm always here to help. And this problem, though, is finished. And like I said, if you wanted to do this with a graphical method, it exists on YouTube, but this was the more precise analytical method. So until next time, adios. Take it easy.